So Albert Einstein accepted the idea as a hypothesis that maybe the way to explain that strange finding of Maxwell's equations that the speed of light is invariant or constant for everyone regardless of how they're moving is the possibility that space and time are not invariant, that they can actually change as a result of relative motion so that they may look different, they may be measured differently for people moving relative to one another. And then he sat down to say, all right, what exactly will we see with these effects on space and time? And he came up with the idea of relativistic effects. Now, these relativistic effects are the effects on space and time, and we'll see later mass and energy, as a result of relative motion. And I want to emphasize that these effects are always there. They always happen. Every time two objects are moving relative to one another, space and time are perceived differently for them, or not perceived, because the effects, as we'll see in a later section when we take a look at some numbers, are very, very small until you get close to the speed of light. And then they start to get noticeable. But they always happen. Space and time are always malleable and are always affected by motion. So what are these relativistic effects that Einstein figured out must be going on? The first one is called length contraction. This is the effect on the space part of space-time. And what length contraction says is that the space of a moving person will actually shorten relative to the space of a stationary person. And the faster a person is moving relative to someone else, the shorter their space becomes, the more length contraction you get. The second effect is on the time component of the universe, and this effect is called time dilation. Dilation is a fancy word for stretching. So what time dilation says is that the time of a moving person actually stretches out, meaning it slows down. A second stretches out to become longer and longer and longer than 1 second relative to a person who's not moving, who's stationary to that moving person. And again, the faster a person is moving relative to another person, the more their time stretches out, the more time dilation there is. So let me illustrate this with a couple of my friends. This is Captain Astro, and this is our alien friend Oobleck. And Oobleck is in his spaceship, but his spaceship, as you'll see, is sitting stationary on the ground, and it's stationary relative to both Oobleck and Captain Astro. What we would say is that Oobleck and Captain Astro are in the same frame of reference, the same stationary frame of reference, because the spaceship is not moving relative to either of them. So if Oobleck looks at his spaceship and measures its length, he measures his spaceship at rest as being 5 meters long. Captain Astro measures Oobleck's spaceship, and because the spaceship is stationary relative to him as well, he measures the length of the spaceship as also being 5 meters long. But he goes further and he makes the observation as well that the clocks on board Oobleck's spaceship are ticking away at the same rate that the clocks that Captain Astro's clocks are ticking away at. Okay? So they are now both in the same stationary frame of reference. But now Oobleck fires up his engines and takes off in his spaceship. So notice now that the spaceship is now moving relative to Captain Astro. They're no longer in the same frame of reference. Captain Astro remains in his stationary frame of reference. but the spaceship is now in a moving frame of reference. But notice also that it's not moving relative to Oobleck. Oobleck stays in exactly the same place relative to the spaceship. So according to Oobleck, he and the spaceship are in a stationary frame of reference, which means nothing has changed because there's no relative motion. And when he measures his spaceship, he sees that it's still 5 meters long. But now that spaceship is moving relative to Captain Astro, and that strange effect of length contraction will start to kick in, because from Captain Astro's perspective, his ship is moving relative to Captain Astro at 90% of the speed of light, that's 0.9 c, and he measures it now as only 4 meters long. The length has contracted, but not only that, but the time on the spaceship relative to Captain Astro's time has dilated. It's stretched out. So the clocks on the spaceship seem to be running slower than the clocks for Captain Astro. It shows 72 seconds. The clock shows 72 seconds passing for every 60 seconds that passes for Captain Astro. So 60 seconds, according to Captain Astro, has been stretched out to 72 seconds. Now for Oobleck, the 60 seconds will still be the 60 seconds. The weird thing here is, if you ask who's right, which one is the real time, which one is the real length of the spaceship, the answer is they both are, because space-time is malleable. From this frame of reference, this ship really is only 4 meters long. But from Oobleck's frame of reference, the ship really is 5 meters long. It covers 5 meters of space in his frame of reference. It covers only 4 meters of space in Captain Astro's frame of reference. And if we go even faster, Oobleck still sees his ship as 5 meters long because he's still at rest relative to the spaceship. They both experience the same relativistic effects. But now, says Captain Astro, your ship is moving relative to me at 99% of the speed of light. So now I measure it as only 1 meter long. And now your time has stretched out so that 5 minutes of my time fits into only 1 minute of your time. Again, who's right? Is this ship really 5 meters long or really 1 meter long? The answer, according to special relativity, is yes. It is both, and what you measure is relative to your frame of reference. Mind-blowing stuff. And in the next video, I'll run you through just a really, really mind-blowing little exercise of how weird special relativity is.